And we're live.
Ready to go?
We're live now. We'll tell you when we're ready to go.
I will sit in silence and drink my coffee. I'm sure everyone loves watching me wipe coffee out of my moustache.
Claims live, we've got a black screen at the moment.
I had lots of trouble receiving it locally, even switching to mobile, whether that's Vodafone or...
1.4G, so we'll see. There we go. Something's definitely happening.
I make 852 now, so... Whenever we get the start, I'll just talk for 30 minutes plus then. That should leave enough for any mucking around at the beginning and time for questions at the end. They're usually about 5 minutes late starting. So.
Well, if Matthew's only just finished, I'm going to fill the room as well.
Alright, I'm just everything.
We just heard you were about to break everything and lost the slides.
Yeah, and I'm not sure why they're not displaying properly now. Oh, it's because I've got the wrong scaling. Just let them know I'm just fixing the scaling and I'll be...
Please speak so we can do a sound check.
1 2 1 2 testing 1 2. Good morning, Bono.
Well, they appear to be receiving the slides there, but what's going out on the YouTube channel is...
Nobody cares. Well, I mean, it's almost an accident that the stream is exposed live.
Yeah.
Actually, no, I thought we're streaming talks live now.
They can hear us as well.
Hello.
We're trying to reconnect to you, but they are still saying technology and knowledge.
Hold on a second, let me...
Got the testing message, it was too loud, yeah?
Testing, testing, 1 2 1 2. Is that a better level?
Looking good now. Please start.
Okay, good morning everyone. Thank you for attending my talk this morning. I'm very sorry that I wasn't able to attend DevConf at the last moment to present in person, but thanks to the magic of YouTube, we can hopefully get through this 40-minute slot without me dropping out or disappearing too much. So I'd like to talk today about a project that I've been working on for well, a couple of years, including the prototype phase, but really most of the work that I'm going to present today has come together in the last 12 months or so. It's available in all distributions that are shipping a recent version of LVM2 and Device Mapper, so Fedora, RHEL 7, there is an update on the way for RHEL 6, and most other distributions that keep fairly close to upstream. So just to kind of set the scene for today's talk and provide some background, the project I want to talk about today is dmstats, or Device Mapper Statistics. Now this is something that exists in two components, a kernel piece that has been around for a couple of years, and the new user space support, which I'll be talking about today. Obviously, I/O statistics are not a new thing. They've been around for many years, really kind of coming together to form the sort of statistics we see today in the 1980s. So obviously this is something that needs kernel support. The Device Mapper case is no different here. So the basic iostats that we have on Linux, the block layer was modified to keep track of certain events. So when an I/O is submitted or when it completes, an event counter is incremented. And you'll see that most of the performance metrics use this very simple counter-based model. So as events occur, the counter is incremented, and we can then look at the counter value, or more importantly, how it changed over a particular period of time to determine the level of activity for different events going on in the system. So the kernel side, as most things in the kernel, it likes to keep things simple, and the counters are all implemented as plain integer values. Now, clearly, when we come to look at this as human beings, or to carry out additional processing and calculation with the data, that may not be the most convenient form to work in. We may want rates expressed in terms of human readable quantities like megabytes or gigabytes, and to have those rates expressed in familiar units of time, per second, per minute, or whatever is convenient. So we need the user space tooling to provide this quantization to time, rate conversion, and also possibly to do higher level tasks, things like aggregation and sorting. If you used some of the more advanced options for iostat that allow you to group devices together, you may be familiar with the kind of ideas I'm talking about here. So to look at Linux in a little bit more detail and what we have today, or what we had prior to the introduction of dmstats, the current iostatistics framework has been present since, well, roughly late 2.4 stroke early 2.5. There are some minor differences between the two, but for today's purposes, 2.4 is kind of historical anyway. So what we have now is a set of 11 event counters. These are documented in the iostats.txt file in the kernel sources or in the package documentation that you'll find on your system. And these track quantities like the number of reads completed, the number of writes completed, the number of queue merges, where we see that two IOs are adjacent, and stick them together to build a larger IO to send out to the hardware. And these low-level raw counter values are then consumed by user space tools, historically primarily the systat package. That includes things like iostat, as well as SAR, the system activity reporter, and its data collector component. Today these tools look a little old-fashioned in some ways. They've been around in more or less the current form for sort of 20 or 30 years if you look back to tools that were available on commercial Unix platforms in the 1980s. They're generally very similar. Today there are also more modern alternatives to these that might suit your uses better. PCP is a project started by SGI. It's short for the Performance Copilot, and it's a fairly large set of tools for everything from data gathering, pulling data into the system, recording and archiving, and then presenting or transmitting that data for further analysis and use. PCP is a large topic, so I won't be going into it anymore in today's talk. There are some good talks on YouTube, and it also tends to come up at conferences, largely because it's a relatively new tool that people, at least in the Linux world, are not so familiar with. There are also higher level management tools, things like the OpenLMI suite, which supports the DMTF SIM data model. These today can also read out the statistics from a Linux system and provide them for further processing and use. So this is the state that we have today, and it's been a good model. It's served us well for a number of years, but it does have some limitations. In particular, there is just one counter set per device. This is regardless of how large the device is or how it's composed. If you've ever used Linux MD or LVM on a system with more than one physical disk, you're familiar with the idea that a single block device may be composed of multiple component devices. Perhaps it's a RAID array, so we're distributing data and possibly parity information within that. Or it may simply be a composite device, for example, a logical volume that has been extended several times so that it has disjoint data regions, possibly spanning multiple disks. In these sorts of situations, it may be useful to have a little bit more insight into particular areas of the disk. Without that, we're just getting very coarse averages over what may be a very large physical device. These counters today are also shared by all users. Now, there's a simple technique used that allows us to effectively share this resource among multiple users without interference. And that is just that the counters never reset. They just constantly increase. And this means that anyone using the counters needs to maintain 2 copies of the data. We need to maintain the last thing that we saw and the current snapshot. And we then take the difference between these two, and that gives us the observations for the current interval. It's a relatively small overhead, but it is an overhead, and it does complicate code that needs to read and manage these values in user space. There's a relatively fixed set of performance counters here as well. This is partly down to historical reasons. If you remember the introduction in 2.4 and the later 2.5 changes, you'll know that they're in different places. The reason for this is that once we introduce a file in proc, and in the case of iostats, this is /proc/diskstats, that becomes part of the ADI, part of the interface with user space. And that means that we can't freely make changes to that to add additional fields. We're somewhat more free in the device mapper world here, in that we use careful versioning of both the interaction with the kernel and the library in user space, which means that we have a much better path to introduce new additions or changes in a controlled manner without breaking older systems. Another limitation of the classical disk stats is that they use the kernel Jiffy counter. If you're familiar with the kernel's timekeeping, you'll know that we have multiple different sources of timing information now. The Jiffy counter is a very coarse millisecond resolution, or I should say roughly millisecond resolution counter, that ticks up traditionally every time the timer tick went off. Today you may not have a regular timer tick, but in principle it's just the same. There are 2 real problems here. Firstly, we have a limited resolution. We can't get better than millisecond accuracy, or precision I should say. And also there's an accuracy problem. Depending on what's happening on the system, and especially in virtualized environments, the Jiffy clock may drift. So this time a millisecond may be a little bit too long, next time it might be a little bit too short. Depending on what you're doing with the data, this kind of variation and jitter may be problematic. The last major problem, there's very little insight into the latency that your I/O is experiencing. We do have some averages produced, so the average service time and the average time that an I/O waits before being issued, but these are just coarse averages. If we're seeing very high rates of I/O, and remember we have devices today that are capable of 1 million or more I/Os per second, this single average value gives us very little insight about how the latencies are actually distributed. And often in today's performance analysis, it's that distribution, at least some overall rough shape, that we're mainly interested in. So this has been the sort of state of I/O statistics support in Linux for some time, and as I said, it has largely served us well. We should examine why today this is becoming a problem, or why we would like to have some more capabilities to get better insight into what's going on today. And a major part of the reason is that the storage stacks have changed. To borrow a phrase, it's not your father's storage anymore. So today we have things like software-defined storage. If you've used things like Ceph or Gluster, you're familiar with the idea here. Rather than building large proprietary hardware disk arrays and presenting them over Fibre Channel or some other standard protocol, we build much cheaper arrays of commodity hardware with locally attached storage, and we then use software and networking to make that storage available to the client systems. We also today see much more heavily tiered storage architectures. One of the first ideas of tiered storage is a sort of layered cache where we have a hierarchical storage model and data is automatically moved between tiers depending on its usage patterns. So we may at the front end have in-memory caches moving through fast local storage like SSD or flash made available over the PCI bus. And eventually we may arrive on something like a tape silo at the slowest, largest end of the hierarchy. Where these tiers are implemented in Linux, we may want to have better visibility into the path of an I/O as it tracks down through those tiers and layers. Obviously, I work on Device Mapper, and two of the major additions in Device Mapper over the last few years have been the addition of caching and thin provisioning targets. The thin provisioning target also is responsible for the much better performance we now have with Device Mapper snapshots. Again, these involve breaking up storage up and assigning certain data to fast, low latency, high throughput storage, while other data is moved out to slower back-end storage. Within provisioning, we may have volumes that are initially only partially provisioned and then become fully provisioned or more provisioned as I/O is sent down to different regions of the device. This is somewhat related to the next point. Now, in fact, the example I have here, which is Rev, predates the thin provisioning capabilities in Device Mapper, and it uses a different mechanism for multi-tenancy storage. This one's an interesting use case for Device Mapper statistics because the way that Rev operates, it takes a single LV, slices that up into pieces, and each piece may be assigned to a different virtual machine. So we do have this situation where we have one block device containing a number of logical disk devices that belong to different virtual machines. Again, this is somewhat related to the container and virtualization world, where we may have many images all packed onto a single device. So this leads us on to what we might wish to monitor and observe on these devices. The first point is the one that the old iostats and disk stats mechanism is incapable of. It's not able to perform monitoring on subregions of devices. We might want to use this to identify hotspots, region of the disk which receives a large volume of I/O and that may be becoming a bottleneck. If we were in some sort of an environment with cache devices available, that's the sort of region that we might consider caching in order to give it a performance boost or to remove a bottleneck. We may also want to carry out object discrimination. So one block device, say if it's got a file system or a database stored on it, is going to contain many different objects. If the file system or database can tell us where those objects are, then we can provide statistics specifically for those regions of the disk that are used by the object. As I mentioned earlier, latency characterization is another important area. One way to make this available is to track some kind of a histogram A histogram shows us directly the distribution of a set of values by dividing the value space up into buckets and then accounting each individual I/O into whichever bucket it fits. We build up an overall picture of how the latency is distributed among I/Os. We may also want to grant different users on the machine access to the statistics facility in a way that doesn't interfere with other users. As we said, the old iostats and disk stats uses this simple trick of global non-resetting counters, but when we're providing some of these additional mechanisms like latency histograms, we need something a little bit more sophisticated for that. And we also want to be able to monitor and potentially respond to the overheads that our statistics collection is imposing, either in memory, CPU, or other terms. Since the device mapper statistics provides much greater flexibility and options, it does naturally impose a higher overhead. We'll take a look at how we can track that in a moment. So I'll press on then to a brief discussion of the dmstats tool. As I said, this is available now in most recent distributions. The kernel side of things has been available since 2013. It introduced the general dmstats interface, which uses the device mapper message facility. It allows us to set up arbitrary regions of devices for statistics tracking, and we can also divide those regions up into chunks. So this was updated in 2015 to add two important new features. These are higher precision nanosecond resolution counters, as well as user-defined latency histograms. So what's available now in current device mapper packages consists of two components: a user space library that application programmers can use to directly access the stats data, and also the dmstats command, which allows us to interact with the facility from the terminal. So the command allows us to create, delete, and monitor regions, as well as to print the current values in their rate converted form as provided by the library. So the actual command interface, if you've ever used the dmsetup program, it's very similar. We have the dmstats command, followed by any options or switches, and then a sub-command to indicate what we want to do: create, delete, and so on. The reporting functions of dmstats use the existing device mapper and LVM reporting framework. So again, if you've used that to set the fields that you want to use, or any sorting or selection criteria, that's also available for the statistics. And there's a manual page with examples and full usage information in the dmstats page. So, one of the main ideas in dmstats is, and I briefly mentioned this on the last slide, this notion of regions and areas. A region is just a range of sectors that we're tracking statistics for, and we can break that down further into areas. What we mean by an area is this portion of the disk will have its own independent set of counters, so we can tell whether there's a lot of I/O happening in one area or in the adjacent or any other area. You can create an unlimited number of regions of any size that you wish. Obviously, these do impose a memory overhead, and you'll be limited by the amount of physical memory available on your machine. There's also a little safety check in the kernel that we don't allow the statistics data to exceed more than 25% of available RAM. So to create a region, we use, oddly enough, the create command. We can control the number of areas or the size of the areas that we create. One thing to note here, you do have to set all the options you want when you first create a region. If you don't and you want to change them later on, it's not a problem. Just delete the region and then recreate it. So if I just switch over to
Candidate lost sound, but carry on.
Okay, I'm getting a message you may have lost sound. I hope not. If not, hopefully you can read my lips. So the reporting, as we saw, we can specify a count. You can also specify an interval. If you specify either one, it will cause the reports to repeat. Otherwise, if we just run the report, you'll get a single snapshot of the current values. Just very quickly take a look at latency histograms. These are one of the most requested features in dmstats. It took a little bit of time to get the kernel side of the support correctly worked out and merged, but this is now available in the current device mapper and LVM2 releases. To specify a histogram, we give the bounds, or the bin boundaries. So we've got an example here with 10, 20 and 30 milliseconds. What that is doing is creating 4 buckets in our histogram, one from 0 to 10, one from 10 to 20, another from 20 to 30, and the final one which is for everything 30 and above. And these will then report either as a relative or absolute count when we use the histogram option to the reporting tools. So if I just switch back to a terminal for a moment. allowing you to carry on and create new regions with new definitions. In future, we've got a number of feature requests being worked on at the moment to add grouping and aggregation so that you can more flexibly combine different statistics, direct integration with the LVM tools, and an automated tool to detect hotspots. And hopefully also in the next batch of updates will be a sort of real-time top-style display for the statistics information. So I'm sorry, I've run on with my talking as usual. So I think we've got about 30 seconds maybe for questions. Do feel free to pass those over. They'll be relayed to me via IRC and my fearless video assistant Mark Flitter in our Farnborough office. So please go ahead if there are any questions.
They've lost sound again. They're switching to voice. They're going to collect questions, and that's it.
Should I stop and start?
They've not said to stop the stream.
Don't honestly know what is up with audio. I'm recording a good level here.
It may have been that end. I'm not sure.
I suspect everyone's walked out by now, so there won't be many questions.
Yeah, do bear in mind we are still live.
I know.
Fair enough.
I wasn't going to start picking my nose. I figured, a little white was...
Fair enough. I'm not sure if they want us to switch to intercall or...
There is a Blue Jeans link that Alistair sent out earlier, but I can't connect to it while I'm...
I can connect to it.
I shouldn't sit there with my arms up, should I?
No.
Doesn't look professional. I kind of feel like switching the video off. Yeah, I'm going to switch to slides only. In fact, I'm going to switch over to the other account.